Welcome to Quiet Car Stories. In this video, we'll take a slow and relaxing journey through the history of cars, engines, and the quiet details of automotive engineering. If you enjoy calm storytelling and gentle explanations, please consider liking the video and subscribing to the channel. It really helps support these kinds of long-form, relaxing documentaries. You're welcome to simply sit back and listen. Whether you're here to learn something new, unwind after a long day, or even drift off to sleep, these stories are made to be enjoyed quietly at your own pace. So find a comfortable position, settle in, and let the sound of the story carry you. Let's begin. There is something quietly fascinating about the way machines evolve, not in sudden leaps or dramatic moments of invention, but in gradual refinement, small, patient improvements that accumulate over decades. The turbocharger is one of those stories. Today, it is a familiar presence in modern cars, a subtle force working beneath the surface, compressing air, improving efficiency, and extracting more power from smaller engines. Most drivers rarely think about it. Some may not even know it is there. And yet, the turbocharger carries with it a long and intricate history, one that begins not on the road, but high above it, in the thin, cold air of early aviation. This is the story of how a simple idea, using exhaust gases to improve engine performance, slowly found its place in the automotive world. A story of engineers, persistence, and quiet innovation. A story that unfolds not quickly, but steadily, across more than a century. Early origins and the problem of thin air. To understand the turbocharger, we begin with a problem. An internal combustion engine depends on air. Specifically, it depends on oxygen. The more oxygen that enters the engine, the more fuel it can burn, and the more power it can produce. At sea level, this works well enough. The atmosphere is dense, rich with oxygen, and engines perform as expected. But as altitude increases, the air becomes thinner. By the early 20th century, this posed a serious challenge, particularly for aircraft. As planes climbed higher, their engines lost power. Less oxygen meant less combustion. Less combustion meant reduced performance. Engineers needed a way to compensate for this loss. The solution would come from a Swiss engineer named Alfred Bucci. In 1905, Bucci patented a device that would later become known as the turbocharger. His idea was deceptively simple: use the engine's own exhaust gases, normally wasted energy, to drive a turbine. This turbine would then power a compressor, forcing more air into the engine. In essence, the engine would breathe more deeply, even in thin air. At the time, the concept was ahead of its era. Materials, manufacturing precision, and engine design were not yet advanced enough to fully realize its potential. But the idea had been planted. From theory to practice. Over the following decades, the turbocharger slowly transitioned from concept to reality. In the 1920s, Bucci's designs began to appear in large diesel engines, particularly in marine and stationary applications. These engines benefited greatly from forced induction. They were large, slow-moving, and capable of handling the additional stresses introduced by turbocharging. The principle worked. Exhaust gases spun a turbine. The turbine drove a compressor. The compressor increased the density of incoming air. More air meant more fuel could be burned. More fuel meant more power. It was a quiet but meaningful breakthrough. However, applying this technology to smaller engines, especially those used in cars, would take much longer. Automotive engines presented different challenges. They operated at higher speeds. They required rapid response. And they needed to remain reliable under varying conditions. Early turbochargers were not yet suited to these demands. There was also another issue: heat. Turbochargers operate under extreme temperatures. Exhaust gases can exceed several hundred degrees Celsius. Managing this heat while maintaining durability and efficiency required materials and engineering solutions that were still developing. So, for a time, the turbocharger remained mostly outside the automotive world. Its potential was clear, but its moment had not yet arrived. The influence of aviation. While cars waited, aviation continued to push turbocharger development forward. During the 1930s and 1940s, aircraft engines increasingly relied on turbocharging to maintain performance at altitude. This was especially important during the Second World War, where high-altitude capability could determine the outcome of aerial engagements. Turbochargers allowed aircraft to fly higher, faster, and more efficiently. They became an essential part of aviation engineering. And with this widespread use came improvements. Materials became stronger, designs became more refined. Engineers learned how to manage heat, pressure, and reliability more effectively. In many ways, aviation served as a testing ground. By the time the war ended, turbocharger technology had advanced significantly. The question was no longer whether it worked. The question was how to adapt it for the road. First steps into the automotive world. The transition from aircraft to automobiles was not immediate. Even with improved technology, turbochargers still faced challenges in passenger vehicles. One of the most notable issues was something now known as turbo lag. Unlike a mechanically driven supercharger, which is powered directly by the engine, a turbocharger relies on exhaust gases. This means there is a delay between pressing the accelerator and the turbocharger reaching the speed required to provide additional boost. In practical terms, this created a moment of hesitation, followed by a sudden surge of power. For everyday driving, this could feel unpredictable. There were also concerns about cost, durability, and complexity. For many manufacturers, the benefits did not yet outweigh the drawbacks. However, the idea continued to linger, and in the post-war years, as automotive engineering advanced, the turbocharger slowly began to find its way into experimental and niche applications. One of the earliest attempts to bring turbocharging to production cars came in the early 1960s. American manufacturers, always willing to explore new technologies, introduced turbocharged versions of existing models. Among them were the Chevrolet Corvair Monza Spider and the Oldsmobile Jetfire. These vehicles represented an important step. They demonstrated that turbocharging could, in fact, be applied to passenger cars. But they also revealed the challenges. The systems were complex. Reliability issues emerged, and the driving experience, while powerful, was not always smooth or predictable. As a result, these early efforts were short-lived. Turbocharging once again retreated, not as a failure, but as a technology still waiting for refinement. A period of quiet development. Through the 1970s, turbocharging entered a quieter phase. It did not disappear. Instead, it continued to evolve behind the scenes. Engineers worked on improving response times. Materials continued to advance, better cooling systems were developed, and perhaps, most importantly, the broader context of the automotive industry began to change. Fuel efficiency became increasingly important. The oil crises of the 1970s forced manufacturers to reconsider how engines were designed. There was a growing need to extract more performance from smaller, more efficient engines. This created an opportunity. Turbocharging, when properly implemented, offered exactly that. It allowed smaller engines to produce the power of larger ones, without the same level of fuel consumption. The idea was no longer just about performance, it was about efficiency. And slowly, manufacturers began to take notice. The gradual return. By the late 1970s and early 1980s, turbochargers began to reappear, this time with greater success. European manufacturers in particular embraced the technology. They approached it with a level of precision and patience that allowed for more refined implementations. Turbocharged engines began to find their way into both performance cars and everyday vehicles. The driving experience improved. Turbo lag was reduced, though not eliminated. Power delivery became more manageable. Reliability increased. What had once felt experimental now began to feel intentional. And with each new generation, the turbocharger became a little more refined, a little more integrated, a little more essential. As the 1980s approached, something subtle began to shift. The turbocharger was no longer an experimental curiosity, nor a fragile, temperamental addition reserved for niche vehicles. Instead, it was becoming something more dependable, more refined, more quietly integrated into the philosophy of engine design. This transformation did not happen all at once. It unfolded gradually. shaped by careful engineering, changing priorities, and a growing understanding of how to harness forced induction in a controlled and predictable way. Refinement and control. One of the most important developments during this period was not the turbocharger itself, but the system surrounding it. Earlier, turbocharged engines had struggled with inconsistency. Power delivery could feel uneven, sometimes delayed, sometimes abrupt. The experience required adjustment. It demanded awareness. But with the introduction of improved fuel injection systems and electronic engine management, this began to change. Engines could now monitor and adjust fuel delivery with far greater precision. Air and fuel could be balanced more accurately, even under varying conditions. This allowed turbocharged engines to behave more smoothly, more predictably. At the same time, engineers worked to refine the turbocharger's internal components. Better bearings reduced friction, improved turbine designs, increased efficiency. Stronger materials allowed for higher operating temperatures and pressures. And then there was the development of the wastegate. The wastegate is a small but essential component. It controls the flow of exhaust gases to the turbine, effectively regulating how much boost the turbocharger produces. Without it, pressure could rise uncontrollably. With it, the system could be carefully managed. This simple mechanism helped transform turbocharging from something volatile into something stable. Motorsport as a testing ground. While refinement was happening in road cars, another world was pushing turbochargers to their limits. Motorsport. Racing has always been a place where engineering is tested under extreme conditions. It is where ideas are accelerated, sometimes literally. And during the late 1970s and 1980s, turbocharging became a dominant force in several racing disciplines. In endurance racing, turbocharged engines demonstrated their ability to deliver sustained power over long periods. In rally racing, they proved capable of handling unpredictable terrain and rapid changes in load. And in single-seater racing, particularly in Formula One, turbochargers reached levels of performance that were, in many ways, extraordinary. Engines became smaller, yet significantly more powerful. Boost pressures increased dramatically. At times, these engines produced outputs far beyond what had previously been considered practical. But alongside this power came challenges. Heat management became critical. Reliability was constantly tested. And the very characteristics that made turbochargers effective, such as delayed response followed by rapid power delivery, required drivers to adapt their techniques. Yet through all of this, valuable lessons were learned. Engineers gained deeper insight into airflow dynamics, combustion efficiency, and thermal control. These lessons did not remain confined to the track. They gradually filtered back into road car development. And as they did, turbocharged engines in everyday vehicles continued to improve. The balance between power and efficiency. By the late 1980s and into the 1990s, turbocharging had reached an important stage. It was no longer defined solely by performance. Instead, it began to represent a balance between power and efficiency, a balance between size and output, a balance between engineering complexity and everyday usability. Manufacturers started to recognize that turbochargers could serve multiple purposes. In performance cars, they offered increased power without requiring larger engines. In smaller vehicles, they allowed modest engines to deliver adequate performance while maintaining fuel economy. And in diesel engines, turbocharging became particularly effective. Diesel engines naturally operate with higher compression ratios and benefit greatly from increased air intake. When combined with turbocharging, they could produce strong torque, smooth delivery, and improved efficiency. This made them especially suitable for long-distance driving and commercial applications. Gradually, turbocharged diesel engines became common across Europe and other parts of the world. They were quiet, capable, and economical. And for many drivers, they simply felt effortless. Addressing turbo lag. Despite all these improvements, one characteristic remained: turbo lag. It had been present since the earliest designs, that brief pause between acceleration and response. For some, it was a minor inconvenience. For others, particularly in performance driving, It was something to be carefully managed. Over time, engineers developed several approaches to reduce its impact. Smaller turbochargers could spool up more quickly, reducing delay, though sometimes at the cost of peak power. Twin turbo systems introduced multiple turbochargers, often of different sizes, working together to provide both quick response and strong output. Variable geometry turbochargers, particularly in diesel engines, adjusted the shape of the turbine housing to optimize airflow across a wider range of speeds. Each solution brought its own advantages, and together they helped make turbocharged engines feel more natural, more immediate. The goal was not to eliminate turbo lag entirely, but to soften it, to make it less noticeable, to allow the engine to respond in a way that felt intuitive. Integration into everyday vehicles. As the 1990s progressed, turbocharging became less of a distinguishing feature and more of a standard option. It appeared in family cars, executive saloons, and compact hatchbacks. Sometimes it was highlighted as a performance feature. Other times it was simply part of the engine design, working quietly in the background. Drivers became accustomed to it. Manufacturers continued to refine it, and gradually the turbocharger became something that no longer required explanation. It simply existed as part of the engine, the modern era and quiet ubiquity. As the new millennium began, the role of the turbocharger entered a new phase, not one defined by experimentation or even refinement alone, but by widespread adoption, downsizing, and environmental pressures. One of the most significant shifts in modern automotive engineering has been the concept of engine downsizing. Instead of using larger engines to produce more power, manufacturers began using smaller engines, combined with turbocharging. The reasoning was straightforward. Smaller engines consume less fuel under light loads. Turbochargers provide additional power when needed. Together, they offer a balance of efficiency and performance. This approach was also influenced by increasingly strict emissions regulations. Reducing carbon output became a central concern. Turbocharging, when paired with precise fuel control and modern emission systems, helped manufacturers meet these requirements. The result was a new generation of engines, compact, efficient, and quietly powerful. Advances in materials and design. Modern turbochargers benefit from decades of accumulated knowledge. Materials are now capable of withstanding extremely high temperatures and rotational speeds. Some turbochargers spin at over 200,000 revolutions per minute. At these speeds, even small improvements in balance and durability can have a significant impact. Ceramic components, advanced alloys, and improved cooling systems all contribute to longevity and efficiency. At the same time, computer modeling allows engineers to simulate airflow and thermal behavior with remarkable accuracy. Designs can be tested virtually before they are ever built. This level of precision was unimaginable in the early days of turbocharging, and yet it has become standard. Electric assistance and hybrid integration. In recent years, another quiet evolution has begun: the integration of electric systems with turbocharging. Electric turbochargers, or e-turbos, use small electric motors to assist the turbine. This helps reduce lag even further, providing boost almost instantly. In hybrid vehicles, where electric motors and internal combustion engines work together, turbocharging plays a complementary role. The electric motor can provide immediate torque. The turbocharged engine can deliver sustained power. Together, they create a smooth and continuous driving experience. Once again, the turbocharger adapts, not as a standalone innovation, but as part of a larger system. A technology that became invisible. Perhaps the most interesting aspect of the turbocharger's journey is this: it has become almost invisible. In the early days, it was something to be explained, justified, even questioned. Now, it is often assumed. Many modern engines rely on turbocharging as a fundamental component, and yet most drivers rarely think about it. It operates quietly, efficiently, without drawing attention to itself. It simply does its work, cycle after cycle, journey after journey. reflective conclusion. If we step back and consider the full arc of this story, a pattern begins to emerge. The turbocharger was not a sudden breakthrough. It was not a single moment of invention followed by immediate success. Instead, it was a gradual evolution, an idea introduced in the early 20th century, refined through aviation, tested in motorsport, adjusted for everyday use, and finally integrated into the fabric of modern automotive design. It is a reminder that progress is often quiet, that innovation does not always arrive fully formed. Sometimes it takes decades, sometimes it requires patience, and sometimes the most impactful technologies are the ones we barely notice. The turbocharger is one of those technologies. It does not announce itself loudly. It does not demand attention. It simply works, steadily, reliably, almost invisibly. And in doing so, it has reshaped the way engines breathe. As the road continues forward, and as automotive technology moves toward electrification and new forms of propulsion, the role of the turbocharger may change once again.